Well, they're not going to see me anyway because I'm going down here. Hi, everybody. How are you doing? Isn't this a wonderful spring day? Oh, I'm sorry. Did I just jinx it? That means we're going to get 4 feet of snow between now and Wednesday, right? Oh, I hope not. Those of you who don't know me, my name's Bernie Van Ness. I'm the chairman of the Hamilton Amateur Astronomers. It's my pleasure to be in that capacity for now. If anybody wants to join, please put your hand up. No? Oh, crap. Okay. Let's see. Now that you know who I am, I don't know who all of you are. There are some faces I don't recognize. If this is your first visit with us here today, or first visit with us, and your first visit is here today, please put up your hand. Let me see. We've got 1, 2, 3, 4. Oh, good. It's okay. I'm not going to make you get up here and do anything for us, except maybe show us a magic trick. No, and you disappearing is not what we want. Those of you who have not been here, and even those of you who have been here, let's see. This is our agenda for tonight. As you can tell, I'm doing our welcome and introductions. I'll run through some announcements, quite a few announcements actually, and then we will have our guest speaker. We'll take a bit of a break and come back, and we'll continue on with the sky this month and a couple other little things. So please don't disappear at the break, okay? Come back in. There's much more to the show. Let's see. Those of you, even though some of you who have been here before don't know where the washrooms are, washrooms are through the doors you came in. Men's is straight across, and women's, if you hang a right and then a left and then a right again, you'll get to the ladies. It's just on the opposite side of the tower. What do we have? We have our librarian at the back there. We have Denise. Wave, Denise. She's way at the back there. She would love to send you home with a book or two. I'd love to see you go home with a book or two. I didn't catch that. Magazines. Oh, magazines as well. Okay, good. Did we expand the library today? Okay, we've got a whack of new books back there. Be sure to check them out during the break or at the end of the meeting. Our loaner program is handled by our good friend and your good friend and my good friend, Paula. Paula, give us a wave so we know where you are. There she is, hiding in the corner. If you're not a member as yet and you'd like to become one, she's happy to take your money. Actually, any of us will take your money. Let's see, what else have we got going back there? Food share is somewhere back there. The food share program last month, we collected $30 in cash and about $12 pounds of food. On that topic, that's awful close. On that topic, we are in need of a basket, bucket, tub, something to put the food in and cart it away with. We also need a bin and a jar, a money jar, preferably non-glass, to put the collected cash in. And while we're at it, we need somebody to volunteer to take over that position, just taking care of the food bank and making sure the stuff gets to where it needs to go. If you are interested in any of those positions, please see, I guess, Paula would be a good person to see for that. Paula just looked at me and went, what? Let's see. In announcements, we have, on InReach, we have the Star Party. How many of you people went to the Star Party in September up north? A few of you? Okay. It has been scheduled now for September 22nd to 25th, same place. Okay, and there'll be a lot more details about that as time goes on, but just mark your calendar now, September 22 to 25. Okay, better start marking stuff off here or I'll forget what I'm doing. This next weekend, we have our scope clinic, our first one in a couple of years. That'll be on Saturday, the 18th, open to the public between 2 o'clock and 4 o'clock, free of charge. Of course, we will gladly accept donations for the food bank again, between 2 and 4. Who's planning to attend? 1, 2, 3, 4, 5. Well, be a lot of walking room. We did that, we did that, we did that. The Event Horizon deadline for the next issue is 26th of February at midnight, if I remember what Bob told us at council. Yeah, he's shaking his head, that's good. And according to Steve, or via Steve, after this meeting today, weather permitting, there will be viewing from the parking lot. Hopefully, we'll get a chance to see the comet. Okay, and Mars. So the comet and Mars. And along that same venue, if the weather holds up and doesn't go sub-zero on us to the point of extreme, I'm hoping to open the park in Binbrook tomorrow evening. That has not been broadcast via Monkey Mail, or MailChimp, sorry. But I will send it out. But right now, it looks like we're gonna go. I just have to go out and make sure the ground's safe enough to drive on without sinking the vehicles. Let's see. And let's see, we've got March the 17th is our first scheduled Binbrook Dark Sky Site date. March the 25th, we will be hopefully again at the Grimsby Welcome Center. That's a public event. Wow, there's a lot of stuff. Let's see, InReach again, Astro 101 is starting up on the 17th, and I believe John Govro's in the background here somewhere. I said he's in the background, so that means he's in Zoom.
I am. I don't know if I can talk.
Go ahead, John. Go ahead, John.
I don't know if I can talk. Can I talk? Can you hear me?
Yes.
I can't hear or see you, unfortunately. So
John, I think he's saying to go ahead.
Oh, okay, wonderful. In that case, hello everybody. Yes, the Astro 101 session for beginners and new people and all that is going to get going. We have a number of people who have signed up, and if anybody else is interested, you're welcome to join in. It's a fun and friendly and casual get together that we do online, so everyone's safe. For beginners, and we cover the very, very basics of astronomy, so that when we have wonderful speakers like we have today that come in and tell us about exciting things, everybody's up to speed and knows the terminology and stuff like that. Or if you're interested in borrowing a telescope from the loaner program, we'll show you how to use a telescope, which end to look through, that sort of thing. So everybody's welcome. All members are welcome. It's fun, it's casual, it's interactive, and you can email me at astro101@amateurastronomy.org, and that email is in the newsletter as well. So if you want to join in, I would love to hear from you. Thank you so much, Bernie. I appreciate the time.
You're very welcome, John. Thank you for that information and for your years of running that program. It gets better and better with age, as do we all. Okay, let's see. Okay. Say something, I'm saying something. No, nothing there? Okay, he's saying try again. Okay, I got a thumbs up from Doug. And I presume we're all good to go to continue on. Okay, when you came in the doors tonight, you saw on our first screen a set of 4 pictures showing groups of clusters. They are a great thing. They are a great, great fun thing to view and find and try to sort out. I'm sure you've seen Markarian's chain, or at least pictures of it, M81 and M82. And the companion, I think, is 3077 NGC. Oh, Bob's shaking his head. That's good enough for me. And Steve's shaking his head too. Good, good, we got it. Our speaker tonight has a much more focused approach to these galaxy groups and clusters than I do. I take mine from a little book like this. This happens to be available from the Astronomical League. Her research is quite extensive. Of course, I'm referring to Dr. Laura Parker at, you're here at McMaster, I'm sorry. I just had a brain fart. That's terrible of me, I'm sorry, but I got it. It says for me to read your bio. I'm not going to read your bio, I'm going to put it up here because I'm sure everybody in this room can read. Oh, where'd you go? There we are. She's a professor and university scholar, although I don't know what the distinction is of a university scholar. You might enlighten me to that, in the Department of Physics and Astronomy. She's been around a while. She's been here, well, not here, but visiting with us previously. And I look forward to hearing more from her. Ladies and gentlemen, Dr. Laura Parker. Now, we need somebody to get you set up.
Yeah.
Okay, who's setting her up?
I should be okay.
Okay, well, I'll take that. Move this stuff out of your way. While she's connecting herself and such, this book, I'm just inviting the group. They can come and take a look at it during the break. Please do not take it home. It's the only copy that I have. And at $20 American a piece, I'd like to be able to keep it at home. Plus shipping, yes. Okay. Are you all up?
I'm all set.
You're all up? There you go. Have fun.
Thank you very much. Okay. Yeah. We're good remotely? Okay. Closer? Okay, testing. Testing again. Testing again. Again. And again. Okay, great. So the people monitoring the remote participants, I have a tendency to move around, and I will do my best to stay parked here. But let me know if I'm wandering too far from the microphone. So good evening, everyone. Very happy to be here. It has been 10 years since I last spoke to this group, I realize. So it's been a long time. And today I want to talk a little bit about my favorite objects in the universe, which are galaxy groups and clusters. But in order to get there, we're going to first do a little bit of an introduction to galaxies. What are galaxies? The different kinds of galaxies. Will that work? All right. So brief introduction here, brief interruption while I try the lavalier. Okay, so testing this. Testing. Okay. Some feedback. Okay, testing. All right. Okay, let's see if my remote will work. Okay. So today, I'm going to talk a little bit about galaxies, what they are, and some of the basic properties. And I'm going to focus for a little bit on some beautiful images of interacting galaxies, because who doesn't love interacting galaxies? And then at the end of today's talk, I'm going to discuss more about galaxies specifically that live in groups and clusters, which is where I spend most of my intellectual time these days. And I'll end with a little bit of some of the current research going on in my group. Okay, we'll be doing some walking back and forth. I might be losing batteries. Okay, so let's start with some beautiful images of galaxies. Some of you will know some of these objects. You may have looked at them before. We have interacting galaxies here, a beautiful spiral galaxy, a beautiful elliptical galaxy. These are all fairly nearby galaxies, so we can see them in lots of detail. I could stare at these all day. I find galaxies fascinating. They're complicated. They have all different shapes, all different patterns, and trying to understand why they look the way they do and how they change in time is how a whole bunch of us at McMaster spend our time. So these are optical images. These are using the same wavelength of light that you see with your eye that you would see if you looked through the eyepiece of a telescope. And what you're not seeing here is all the other wavelengths of light. And that's going to come up a couple of times during the talk, that we can learn more about objects in the universe if we look at all different wavelengths. So when I say all different wavelengths, I mean X-ray telescopes, ultraviolet telescopes, infrared, and all the way out into the radio, where I'm going to end today. So I want to know, why do some galaxies look so smooth and boring and plain, and some galaxies have these beautiful spiral arms with these dust lanes, and how do those things change over time? Okay. The other thing that I want to highlight, which is not the focus of today's talk, but is another area of my research, and something I did talk to this group about a decade ago, is that when we see a visible galaxy, and this is just a cartoon of a galaxy, when you see a galaxy like that, you have to remember that what you're seeing is the tip of the iceberg, and the visible part of a galaxy is a small fraction of the total size of a galaxy. So in the middle of this huge blue object here, I have a visible galaxy, and the blue blob here is representing what's called the dark matter halo. So I'm going to flash this up and then tease you and not talk about it for the rest of today. But if anyone wants to know about dark matter, that's another one of my areas of expertise, and I'm happy to talk about it. But what I would like you to take away from this section is every time you see a beautiful galaxy like that, you are not seeing the whole picture. That galaxy is embedded in a much larger structure, which is really, really massive. Most of the mass of a galaxy is in the dark matter, and not in the part you see with your telescope. So you can think about really galaxies that you see, the visible part being the tip of an iceberg, and the rest of the galaxy is dark matter that you can't see. And that matters because it has mass, it has gravity, so how things move in the universe is dominated by this dark matter, because that's where the gravity mostly comes from. Okay, so galaxies are not static objects, they change in time. And so we call that galaxy evolution. And unfortunately, as somebody who studies galaxies, I cannot watch a galaxy evolve. I wish I could, but all of the processes that are relevant are much longer than a human lifespan. So simulators, people who use computers, can try to model how galaxies evolve, but we can't see galaxies evolve. So we have two approaches to studying galaxy evolution as observational astronomers. One is what is sometimes called galactic archaeology. And to do that, what we do is we study the oldest things around us, like for example, in our own galaxy, the Milky Way, and try to figure out where they came from. So you see today the end product of galaxy evolution, and you try to figure out what must have happened to get us there. So that's one approach. Another approach, which is the one I take more often in my research, is to look back in time. And we're so lucky as astronomers that every telescope is a time machine. As we look at ever more distant objects, we're looking back in time. I'm making this really difficult for the AV folks by moving around. I apologize. And so by using telescopes as time machines, we can look back in time and we can see what things looked like in the past. So what I mean by time machine is everything we look at in the universe, we're looking at it as it was in the past. And the further away an object is, the further back in time we're looking. And so the galaxies I'm going to show you today are mostly millions. Some are going to be billions of light years away. So I'm looking back in time to when the universe was younger. And the galaxy population, if it changes over time, the galaxies 1 billion light years away will look different than the galaxies 2 billion light years away and 3 billion light years away. So although I cannot see an individual galaxy evolve, I can see the population evolve. And that's what we do in my group. All right, so some basics on galaxies. This is a modern version of a famous classical plot. I would not be surprised if you take Astronomy 101, if you see something like this. This diagram is called the Hubble tuning fork, named after Edwin Hubble. So back in the early days of studying galaxies, when people first realized that these beautiful collections of stars and gas and dust were actually outside the Milky Way, there was an attempt in the early 20th century to classify these objects. And so Edwin Hubble drew this sequence of different galaxy types in the universe, ranging from what we call elliptical galaxies on the left through to the beautiful spiral galaxies on the right. And there's a fork in this Hubble tuning diagram where the galaxies on the top part do not have bars in their center, elongated structures in the center, and the ones on the bottom do, as you can see, the S capital B, the capital B stands for a bar. And so we like to, as astronomers, classically, we like to put things in bins and give them names, but really this is a continuous distribution of galaxies, ranging from galaxies that are fully three-dimensional. So an elliptical galaxy is like the stars are moving like a swarm of bees. So it's a three-dimensional object. Going through to, as we go towards the right, and the spiral galaxies, those are very much two-dimensional objects. They're like a frisbee. You look at them face on, they're very big, but if you flipped them by 90 degrees, they'd be thin like a pancake or a frisbee. And so these are three-dimensional, and as we go to the right, these are giant elliptical blobs. Here, these galaxies have big elliptical blobs in the middle and a thin part of a 2D structure. These have slightly smaller three-dimensional bulges in the center and more of a two-dimensional disk on the outside. And as you go all the way to the right, you get pure disk objects. The other thing that's really important as we go from left to right in this tuning fork diagram is that the galaxies on the left, you can tell by your eye, they're all kind of orange. That orange color is telling you about the stars that live in those galaxies. So young stars, a galaxy that is forming stars, the brightest new stars that are born are bright blue. And those stars, it turns out, don't live very long. They blow up as these things called supernovae. And so if you've had a galaxy that has had no new star formation for a long time, the blue stars are all gone, and you're left behind with red stars. So when I see a galaxy that looks red or orange, I know it hasn't formed stars anytime recently. As I go to the right, the galaxies get bluer and bluer and bluer. That's telling me they have more and more recent star formation. And so we're trying to understand the why behind this. So you can put things in bins, but it's interesting to understand why they look the way they do. I'm in a physics and astronomy department. We want to understand the physics of these objects, what drives their evolution. So one more slide on the two main kinds of galaxies. So keep in your mind, you've got two, although there's a diversity of objects, you've got two main classes. The three-dimensional elliptical objects on the right, Stars are on random orbits. There's very little gas, very little star formation. They're just balls of stars orbiting around, all within dark matter, which we don't see. And then on the left, we have a spiral galaxy. Spiral galaxy is the Frisbee one, and the stars in a spiral galaxy are orbiting in the disk, in the plane. This is us. So we live in a spiral galaxy called the Milky Way. We live about 2/3 of the way out one of the spiral arms. We're happily orbiting around the center of our galaxy about every 220 million years. So that's about how long it takes us to go around. Now, what's interesting is that trying to understand how these different kind of galaxies form, we've come to learn and realize through both observations and simulations that if you take two galaxies like the one on the left, two nice spinning disks, like two Frisbees that are spinning, and you collide them together, all of that nice ordered rotation gets all messed up, and you end up with a big three-dimensional blob. And so if you take two spiral galaxies like this and smash them together, you can get an elliptical galaxy. So the interactions between galaxies are an important part of their evolution. So just to see a cartoon of that, remember galaxies live within bigger structures called dark matter halos. I take two nice blue spirally galaxies, collide them together. It takes a while for them to interact. This is where the beautiful pictures come in. We're going to see some. And then the end product, if you can wait for 1 billion years or so, 1 to 2 billion years, you'll end up with an elliptical galaxy. So two blue spiral star-forming galaxies use up all their gas in the merger, as we're going to see, and you end up with a red, what we call a red dead galaxy at the end. And what happens if you smash together two red dead galaxies? You get a bigger red dead galaxy. Because what happens, the merger product depends on what goes into the merger. Two nice disks will get randomized and you'll end up with a 3D object. If you already have a 3D object, it's just going to grow as you smash them together. So when galaxies collide, you get some of the most spectacular images, I think, that we have. So here's a real example from the Hubble Space Telescope of interacting galaxies. And what's really neat about studying collisions of galaxies is that the different parts of galaxies react differently when they merge. So if I could simplify galaxies into their three most important components, you've got the dark matter, you've got the stars that you can see, and you've got the gas in the galaxy. It turns out gas is what also will make the stars. So you've got gas, stars, dark matter. To first approximation, both dark matter and stars are what we call collisionless. So what that means is if you picture the dark matter or the stars in a galaxy to be like little marbles, and to have these two galaxies filled with little marbles and I throw them at each other, the distance between the marbles is so big compared to the size of the marbles that they never collide. So they feel each other's gravity and eventually will merge into one object, but the individual stars never collide. So the probability of two stars colliding in a galaxy merger is infinitesimally small. So that's kind of boring, nothing happens. The gas, on the other hand, is collisional. So this, I want you to picture the gas in a galaxy being like a cloud. So if we've got one big cloud over here and one big cloud over here, if they smash together, they're going to interact, and there's going to be a lot of activity when you throw two clouds together. So when I throw two galaxies together, the stars just pass by, the dark matter just passes by, the gas gets stuck, collides, and interesting things happen. In particular, it turns out that when gas is compressed, which is what happens during these collisions, it's more likely to collapse under gravity and make stars. So the way we make stars is gas has enough gravity that it collapses and will make stars. That is favored in these collisions. So when you see two galaxies colliding, you often see a really bright spot in between. That's where there's a lot of star formation happening. Or sometimes you see it in the cores of the galaxies that are merging. That's star formation happening. So just to show some more beautiful examples of these kinds of things, the interacting galaxies are pretty common. Here's a famous example called the antennae. And if we zoom in on the center, which is the field of view of the Hubble Space Telescope, doesn't see all of the antennae. Of the field of view of the main imagers on Hubble is a smaller field. It gets the central region of the two merging galaxies. So if I went back in time 2 billion years, those would be 2 Milky Ways, 2 regular spiral galaxies that look like those frisbees. They don't look like that anymore because we're catching them in this moment that they're strongly interacting with each other. And if I came back in 1 billion years, that would be an elliptical galaxy. So in the past, they were 2 happy spirals on their own. We're catching them in this moment of collision. And in the future, they're going to be an elliptical. And this is one of those nice multicolor images that shows you the importance of multi-wavelength astronomy. So we've got the Hubble image, which is colored yellow in this combined image here. We have infrared, which comes from hot dust that's glowing in the red. And then we have X-ray from the Chandra Space Observatory, which is actually, some of those dots are showing us what are called X-ray binaries, which are actually black holes with little companions. So antennae are one of the nearby colliding galaxies that have been studied a lot. Another famous one are the mice, another beautiful system to try to image. And what I want you to take away is that these kind of things are not rare. So here's a whole photo gallery from the Hubble Space Telescope of all different interacting galaxies. And so we have this problem as observational astronomers that we get one snapshot because the time scale over which things evolve is so much longer than a human lifetime. So we never see one system evolve, but we can see tons of systems. And so by looking at these large collections, we can start to deduce what's going on for the evolution. So we can never see one merger happen, but if you find all different mergers in all different stages of their interaction, you can start to figure out, on average, what's going on. Okay. Oh, and a little note. What I've been talking about here is also our future. So this is not a real image. This is a simulated view of the night sky in the future because we are on a collision course with our nearest neighbor. So the Milky Way is this nice spiral. Nearby, we have Andromeda, another beautiful spiral galaxy I'm sure almost all of you have seen before. If you look at the night sky today, Andromeda is this faint little smudge. We all wish it had a slightly higher surface brightness so it was easier to see with our naked eye. But as time goes on, and I'm talking over the next hundreds of millions of years to billions, next few billion of years, Andromeda is going to get bigger on the sky because we're moving towards each other at hundreds of kilometers per second. And eventually, our galaxy will merge with Andromeda. And we are going to end up being in a giant elliptical galaxy. And then the night sky is going to be really bad for studying deep sky objects. The Earth is not going to be habitable at that time. The sun will have ended its life, so this is not particularly relevant for us. But in about 4 billion years' time, about the time that our sun will run out of energy, it's predicted that we will be in a giant elliptical galaxy. And so that means we'll be in the middle of a three-dimensional object. Right now, the reason that I can study these things is because we live in a frisbee. So I don't look within the frisbee to study distant galaxies. I look above or below the plane of the Milky Way. If I live in an elliptical galaxy, I can't do that. So we should feel fortunate. If you want to take these nice pictures of galaxies, we're pretty fortunate that we live in a spiral galaxy and not an elliptical. Okay. Other little note to add is that our whole universe has been expanding since it formed. And so that means over time, things are getting more spread out. So collisions are actually, and these mergers are less common today than they were in the early universe. And so as we get more images from JWST of early galaxies, we can expect to see more things like this. This is the Hubble Space Telescope image of what sometimes is called the spiderweb galaxy. It's actually many little tiny galaxies that are all merging together at once. And we think this was really common in the early universe. The whole universe was just smaller and denser. So the distances between galaxies was much smaller and there was a lot more interaction. So expect to see more of those from JWST. I have so many pretty pictures that I could talk about all night. This is my favorite galaxy. This is the Cartwheel Galaxy, which is, again, one of these nice multi-wavelength images. But what's happening with this is this big spiral galaxy would have been a normal spiral galaxy not that long ago. A little galaxy punched right through the middle of it, one of these companions, probably this one, although not 100% for sure, went right through the middle of the disk of the big galaxy, and it pushed a bunch of gas outwards, and you got this ring of extra density of gas, which started to form stars and made that beautiful ring. So the interactions between galaxies I find fascinating because they give us objects like this, and another one that has a ring of star formation is called Hoag's object. Just amazing, amazing objects come from mergers and interactions. Okay, so galaxies are beautiful, galaxies are diverse, galaxies interact. They interacted more in the past. They also interact more when you're in an intrinsically denser environment. So we classify galaxy environments as being one of three rough environments, although again, it's one of these things that is a continuum, all the way from very isolated galaxies through to little collections of galaxies we call galaxy groups, through to the densest places in the universe, which are these rich galaxy clusters. Isolated galaxies are amazing. They're also dynamic. You leave a galaxy all by itself, it doesn't stay the same, it changes. Changes because it starts to use up its gas, it changes if it has a black hole in the center. So that's interesting, but I am more interested in my research on what do the special effects of living in these overdensities have on galaxies. So what is special to your evolution if you live in one of these environments? And to be honest, most of my research in the last decade has focused on galaxy clusters, which are the richest overdensities of galaxies, and they're amazing. But what you can already tell by eye in that picture is that most of the galaxies are red and dead. So remember I said when you see an orange or a red galaxy, that's telling you there's been no recent star formation. Whatever evolution has happened in these galaxies has mostly already happened. And we think a lot of that evolution happens in groups. So I love groups. It's where I started. My very first paper in my PhD was on galaxy groups. The problem is they're harder to study because they're harder to find. If I take a picture of a deep field with a telescope like Hubble and I see a bunch of orange galaxies, I know there's a cluster there. Groups are diverse objects. Some of them have a bunch of spirals like this one. Some of them look like little mini clusters filled with red and dead galaxies. They're extremely diverse, which means they're really hard to find. They also, when I see a collection of 4 galaxies like that, how do you know that they're actually feeling each other's gravity, that they're actually close together in real space? So this is a flat picture, right? Those galaxies could be at wildly different distances. So to study groups, you can't be content with a picture, like with clusters. You have to precisely measure distances to each galaxy and figure out, are they actually at the same distance? And that is one of the hardest things in astronomy, is measuring accurate distances for large numbers of objects. And so that's what we spend a lot of our time doing. Before we can do the cool science, we have to measure the distances to objects. And I couldn't talk about groups without flashing up a recent image from JWST. For those of you who have been following the releases of images, this was part of the original release of the 5 first images from JWST. And we actually saw an image of this group at the beginning. If you came in early before Bernie started speaking, he had a picture of Stephan's quintet. This is Stephan's quintet in the infrared from JWST. It is an amazing image of, it's called a quintet, but actually this galaxy is not interacting with the others. It's in the foreground. It's just chance projection on the sky that it looks like it's at the same place. The other galaxies are bound to each other, moving around each other, and you can see all of this nice debris that's being ripped out of galaxies. You've got star formation actually happening here, not within any of the galaxies, but in the space between the galaxies, which is very cool. And while I'm at it, I'll flash up one more cool picture from JWST, even though it's not relevant for today's talk, just because I love it. This is a perfectly face-on spiral. So picture our Frisbee, perfectly face-on, and zooming in, so you're really seeing the spiral arms and all the structure with JWST. We're getting images like this every day being sent down from nearby galaxies. And there's just such a richness of data coming from JWST, so much cool science to do. When I first saw this image, the thing that got me incredibly excited was this empty spot. So why is there this big dark hole there? It turns out that there's theoretical predictions for this, and now this is the first really clear observation of this from JWST. What happened here is somewhere in this spiral arm of the galaxy, there was a lot of star formation, and when you have a lot of star formation, you also have a lot of supernova explosions. And so the supernovae pushed the gas away, pushed the dust away, and you end up with this big hole. And so we have a bubble there with very little stuff in it. So that's my JWST advertisement. Now back to groups and clusters. So I think groups are the most interesting environment. I wish I had bigger study samples of groups, and that's what we're working on. They're interesting because that's where we think a lot of evolution happens. And one of the reasons is because galaxies like to interact when the motions between them are not too high. So if we've got two galaxies going by each other, if they're going by relatively slowly, say about the same speed as their own internal speed that they're rotating, for example, then they interact really strongly. If galaxies fly by each other really fast, they don't have much effect on each other. And in galaxy clusters, the galaxies move around so fast that they actually don't interact that much. Groups are this sweet spot where the galaxies really interact strongly. Also, if you care about the Milky Way and our own galaxy, we live in a small group with two big galaxies, Andromeda and the Milky Way. So this is really the most common environment in the universe. So if you want to understand galaxy evolution overall, you should study groups. The problem is they're hard to find. So this is a deep field taken from the Canada, France, Hawaii telescope. It's filled with groups, but you don't see them. The only way to find groups is to precisely measure distances to every galaxy in a field and find galaxies at the same distance. So that's the challenge. And just to show you some examples, here's a zoom in on one piece of a Canada, France, Hawaii telescope field where we measured what's called the redshift, which is a proxy for distance of all the galaxies. And there's a little group there with 3 galaxies at a redshift of 0.2, which is at a distance of about 2 billion light years away. You would never have known there was a group there if you hadn't precisely measured all the distances. So this is laborious work, and this is what we have to do to find these big samples. And that was one example. Here's another field with a bunch of groups in it. So if you measure the redshifts, the distances to every single galaxy in a field, you'll find there's lots of little groups, little collections of galaxies. And they're actually on top of each other because they're at different distances. So in a flat picture like this, you'll have tons of groups that are even on the same location projected on the sky because they're at vastly different distances. So this is the hard work we do, and we do it because we want to understand how galaxies evolve in this environment. So in my research group, we study these groups and also clusters all the way from nearby out to pretty big distances, out to about 10 billion light years is our record. And what we're interested in is what happens to galaxies and also their dark matter, which is not in focus today, as they fall into groups and clusters and as they move around and orbit within groups and clusters. So I say what happens to galaxies, we study their star formation and how much they're forming stars. We study their morphologies. Are they spirals? What are the properties of the spirals? And also, we study the properties of their central supermassive black holes, which if anyone has questions on, I'm happy to answer. We really want to understand how this evolution goes from the early universe until today. And just to show you another nice motivating image for why I think groups are so interesting, these are Hubble Space Telescope images of 2 groups that are at a distance of about 5 billion light years, so pretty far away. But these are 2 galaxy groups that have the same mass. So the dark matter halo they live in is the same size, so they have the same mass. They're at the same distance. And this one is dominated by S0 and elliptical galaxies. And this one is dominated by young spiral, lots of fluffy spiral arms and star formation. So a lot of early work in this field said galaxy properties are set by what redshift you find them at and how massive they are. These are 2 groups of the same mass, at the same distance, and the galaxy populations are totally different. And that's what, for me, is a fun mystery to try to understand. So far, just one highlight of what we found is if you take a galaxy of the same mass and you have it all on its own versus as a member of a group or a cluster, Galaxies living in groups and clusters have less star formation. They're more likely to have a big bulge, so big three-dimensional component. And little galaxies, low-mass galaxies, are the most affected by their environment, which is not surprising. Take a big galaxy, it has lots of its own gravity, it can kind of handle itself in this big, dense environment. A little galaxy can get torn to shreds as it falls into a group or cluster. So there's lots of cool physics that happens in these dense environments. So there's a whole bunch of different processes that are unique for galaxies that live in overdensities, like groups and clusters. You can have flyby interactions, which led to the beautiful cartwheel galaxy. You can have galaxies merging, like we've seen examples of. You can have stuff stripped out due to tidal interactions. That's what's happening here. And you can also have interactions between the galaxies and the gas that's in the galaxies. And so that's the bottom two here. So I'm not going to go through all these today. I want to focus on one of these, which is something we're working on, and it's also, you're in luck, the most beautiful. So the process I want to talk a little bit about today is called ram pressure stripping. And so this is a term which describes what happens when a galaxy like this one falls into a galaxy cluster. So this is my cartoon. And remember, a galaxy is stars and gas living in a dark matter halo. As that galaxy falls in, if it has gas in it, the gas will feel a wind from the motion through this galaxy cluster. And so we've known about this for a long time. These are older observations showing a spiral galaxy in the Virgo cluster, nearby galaxy cluster, and the stars are the grayscale image. So this is an R-band image showing us the stars in the galaxy, and the contours are hydrogen gas. And if the hydrogen gas lived in the same place as the stars, like it normally does, they would all line up along this disk, but the gas is being blown out of the galaxy. And the other important piece to know is the center of the Virgo cluster is down here. So this galaxy is moving towards the center of the Virgo cluster, and the gas is being blown out of the galaxy. If you don't have gas in your galaxy, you can't make any stars in the future. It's gas that gets turned into stars. And so what we're doing here is removing the fuel for star formation. So this is one of the ways we think the environment really affects galaxies. So this is an older image. I'll show you some beautiful newer ones. So these are two more examples of so-called ram pressure stripped galaxies. These ones have now been coined, given a special name called jellyfish, and I think you can probably get a feeling for why they're called jellyfish galaxies. Again, you have an optical image which is showing you where all the stars are. And then behind it, you have, in this one it's red and this one is blue. Those are actually taken, the red on the left and the blue on the right is showing you emission taken through a filter that sees H alpha. So I know some of you have H alpha filters that you use when you're taking images. It shows you where there's hot gas in these objects. And so the gas is being stripped out of the galaxy, and then it's being lit up by some energetic process, probably star formation, is making the H alpha that we see there. So these jellyfish galaxies, we now have lots of examples of them. And in my group, we're trying to understand, it's fun to study the individual ones, and they're really amazing. But we're trying to understand how significant is this process on average for large populations. Like, it's nice to find one-offs, but it's also really nice to understand, is this an important mechanism for how galaxies evolve overall? And I couldn't give this talk without showing you the most spectacular one. So this is an object, this is a spiral galaxy in the Coma cluster. So the Coma cluster is the nearest really massive galaxy cluster to us here at Milky Way. The nearest cluster to us is Virgo, and we saw a picture, we've seen a couple of pictures of Virgo, first from the initial slide when you came in, and then I showed an example earlier from Virgo. This is Coma, which is an even bigger cluster than Virgo. This galaxy, this is an optical image showing you where the stars are. This is an H alpha image. This is like 65 kiloparsecs long, at least, for those of you who know astronomy units. Way bigger than the galaxy. This is gas that has been dragged out of this galaxy as the galaxy orbits in the Coma cluster. So spectacular. And we're trying to still understand why it's so collimated. That's kind of strange. What's going on in this system? So for reference, this is an optical image from Hubble, and this is an H-alpha image taken with one of the most sensitive telescopes on Earth, the Subaru Observatory in Mauna Kea. They have a beautiful wide field of view camera and a filter that finds H-alpha at the redshift of coma, which is really important. So we've been trying to find these Ram pressure stripped galaxies in big numbers. And so these kind of objects are pretty rare. But what we do have access to are huge amounts of optical imaging. And so the best way to find these tails is to have measurements of the gas. We don't have gas measurements for so many. So in my research group, one of the things we tried to do is see, could we see hints of Ram pressure stripped galaxies by little star tails, little bits of in the optical, the visible part of the spectrum that could show us that something interesting was going on. This is not particularly a Ram pressure stripped galaxy, it's just to show you the quality of the imaging we get to do this from the Canada, France, Hawaii telescope. The biggest survey ever done of the northern sky, the most imaging we have is from the Sloan Digital Sky Survey. But the telescope used to do this is in New Mexico. It's only a 2-meter telescope only. But it's not the best sky conditions, so the seeing is usually about 1.5 arc seconds, which is great, but not good enough for really seeing structure in galaxies. And so what we use, the same parts of the sky, big sections of it have been imaged with the Canada, France, Hawaii telescope, which is a almost 4-meter telescope, has a huge camera, sees 1 square degree at a time, and our average seeing is about 0.6 arc seconds, which is pretty darn good from Earth. For those of you who do astrophotography, 0.6 arc seconds of seeing is really amazing. So what we've been doing is looking at huge numbers of these little thumbnails and trying to find the galaxies that look like maybe they're starting to be these jellyfish. And then once we find interesting targets, then we follow them up to try to measure the gas. So here's one little example. Little tiny dwarf smudge of a galaxy that has this extension in this direction. So we're predicting that this one probably has a tail. And we did this. This is one example from the Coma cluster of galaxies. We found all the galaxies that we see in the optical have a hint of a tail. And then those give us good targets to follow up at other wavelengths. And so here again is the Coma cluster. And here's one of our galaxies that we thought had a tail. And then a radio observation from an observatory in the Netherlands that shows massive tail of gas. So those contours are showing you the gas. This is an object where the gas is being stripped out of the galaxy. And luckily, it's not just the one good case, I'm showing you one, but all of the ones that we find optical tails seem to have gas tails. And so we found this efficient way of finding these jellyfish galaxies so we don't waste telescope time looking at bad targets. Just to show you some more. These are, again, galaxies we identified in the optical, looking like they probably had some stripping going on, and then in the red, that's radio emission from this observatory in the Netherlands called LOFAR. Big gas tails coming behind these galaxies. So this is one of the things that we're studying a lot in my group right now. The reason we care so much about this is that we're trying to understand how galaxies evolve in groups and clusters. And one thing we learned early on is that galaxies in groups and clusters have less star formation. Why do they have less star formation? Because their gas is being ripped out of them. And we now have nice observations of that to confirm that idea. And then I'll finish today by coming back to the Virgo cluster. So we have a large program, it has many people. I'm one of about 25 active astronomers in this project, but it was led by actually a postdoc at McMaster University, studying 50 galaxies in the nearby Virgo cluster. So Virgo is, again, the nearest cluster to us. It has M87 in the center. If you followed the news in recent years and these amazing discoveries from the Event Horizon telescope of studying right down near a black hole, the first one was M87 in the middle of the Virgo cluster. This is one of the most studied clusters in the universe. So you might ask, what more is there to learn about the closest cluster to us? Don't we have a lot of data? We have a lot of data, and the one thing that was missing was a study of cold gas. It turns out cold gas is what's most important because it's cold gas that directly makes stars. So if you want to understand star formation and how galaxies evolve, you need to understand the cold gas. And the reason why it was so hard to do that is there weren't any good telescopes to do it until recently. And now we have in Chile this amazing array called ALMA. So ALMA is this array of telescopes, and when you put together many telescopes, they can triangulate and give really high resolution. So for 50 galaxies in Virgo, we have beautiful ALMA data. This was the first what's called a large program by any Canadians with ALMA. So ALMA is super, super competitive. The way we get telescope time is you write a proposal, and most of the time you have to deal with rejection. Some telescopes you have to deal with a lot of rejection, and ALMA is one of those. It's so oversubscribed. Only at most 1 in 10 proposals get their telescope time. Hubble is about 1 in 10. JWST is about 1 in 40. So you could have an amazing idea. It really should get done, but there just isn't enough time on JWST to do everybody's science. So ALMA is similar. About 10% of proposals are successful. This was the first large one in Canada that was successful. For each galaxy, we get maps of the cold gas. The upper right little panel here is actually showing you the velocity of the gas. So the blue is coming towards you, the red is going away from you. So that's showing you how that galaxy is rotating. And for a bunch of these galaxies, we are seeing the cold gas also being offset from the stars. So the gas is being stripped out of these galaxies. So we have published the first couple papers, but this is what many of us are really busy on right now, is studying these galaxies in detail with this beautiful data from ALMA, which is a brand new thing on the scene. Okay, so I wanted to leave lots of time for questions. Also, feel free to ask beyond what I talked about too. Anything about galaxies, the universe, I'm happy answering about anything. But I hope I have conveyed that it's a really exciting time to be working in this field. We have all these different telescopes operating at different wavelengths. Galaxies are not individual island universes that live all on their own, but they interact, they merge, they have exciting interactions with their nearby neighbors. Although a lot of my research has focused on clusters, I think galaxy groups are the most interesting environment. That's what we live in here in the local group. That's where most galaxies in the universe live, and that's where mergers are the most common. So we're now at a point where, because of large surveys, we have bigger samples and new observatories that we can study at different wavelengths. There's a lot more to come, I think, on galaxy groups in the next decade. So maybe I'll come back in 10 years again and talk about all the stuff we've learned about galaxy groups. So I'll stop there, and I'm happy to take any questions. Yeah?
You're talking about the dark matter, and I don't know, I guess something I never thought about is, well, maybe with the interacting galaxies, I don't know if they can measure it with the gravitational waves. I guess that's my question, because I guess most of you seem to be talking about different electromagnetic waves.
So dark matter is the dominant mass component, and we can detect it through the gravitational interactions between galaxies. We can figure out how much dark matter is there. Your question is, can we detect it with gravitational waves? And unfortunately, dark matter is too fluffy. So the way to detect gravitational waves is to have incredibly compact objects that are extremely close together and are accelerating. And dark matter is too fluffy. So it doesn't create big enough ripples in space-time that we can detect it with gravitational waves. I wish we could. Yeah.
Very quick question. My understanding is that, as you mentioned, the universe is expanding. What is causing the expansion? My understanding is dark energy, what they call it. But do we understand what dark energy is, and also what's creating the speed of the galaxies for, the movement? I guess that's the questions.
That's an excellent question. Number one, even if we didn't have dark energy, the universe would still be expanding because we started from the Big Bang. So the Big Bang, which happened 13.8 billion years ago, there's initially a lot of energy that's still there, and the universe was expanding. Dark energy is an extra component of the universe, and I'd be happy to come back and talk about that again because it's been a long time. Dark energy is this extra energy in space, which only really became important about 5 billion years ago. And that's causing the expansion, the universe not just to expand, but for it to accelerate. And at the moment, we don't know what it is, but all of the observations are consistent with it being some amount of energy per unit of space. So as the universe has gotten bigger, there's more volume, there's more units of space, so there's more dark energy. But that's a weird concept because any of you who remember your high school physics, you learned about conservation of energy. So where does extra energy come from? It's mind-blowing, but that's what is consistent with all the observations. So conservation of energy doesn't apply on the scale of the universe. So that was your first question, and the second part was about the motions of galaxies. One thing I wanted to point out is that the expansion of the universe is happening on large scales, but nearby, you still feel the gravity of your neighbors. And so your local motion is dominated by the gravity of your local environment, and it's only once you get to bigger scales that the expansion dominates and takes over. So things in a galaxy cluster are always going to be in a galaxy cluster. They're not going to expand away from each other. They're gravitationally bound. Yeah.
Two questions. Okay, the question is, one, what real effect do you expect for astronomy when all the satellites get in place? And what do you expect the effect will be for your astronomy?
So the Starlink satellites, which are being launched in huge numbers, there's some hope that at least the future ones will have a lower albedo, so they won't be quite as bright as the current ones. So for those of you who don't know, these satellite communication satellites are being launched in huge numbers and creating light pollution on the night sky, particularly at dawn and dusk. So when the sun is more likely to reflect off of them, so that's a problem. For amateur astronomers, I mean, you tell me what the effects will be for you. For us as professionals, it's the wide field imaging surveys that take long exposures. They are just being polluted by streaks. And so, of course, we can process them out with image processing techniques, but you lose information. And so it is a problem, and there's a lot of lobbying going on by professional astronomers. And the US has just recently passed some legislation to put some limits on some of this. But the US is one country, space is for everyone. And so one country limiting what can happen is not going to change, I think, the night sky that much. So it's a big problem. And all of the future generation of surveys are doing contingency planning right now. Basically, it's going to take longer to do the same surveys we had planned because you're polluting every image with these satellite streaks.
I was wondering, how do you distinguish between a black hole and a supernova through the gas of a galaxy?
So what we were seeing in that image where I was excited by this big area, what we were looking at was a picture of gas and dust, and it was evacuated. So something had pushed the gas and dust away. Black holes are physically much smaller objects. So we have, other than the Event Horizon Telescope, which is the only time have we ever taken a picture close into a black hole, every other image you see here, the black holes are smaller than a pixel, and we are not resolving them. They are tiny, physically tiny objects. Lots of gravity, but in a very small package. So we don't see pictures of black holes in any of this, unfortunately.
Proximity of galaxies when in clusters and considering how large the dark matter halos are around those galaxies, is there even more interaction between those halos than what we see in optical wavelengths? And do these interactions shape the halos? Do the interactions shape them?
Okay, so galaxies have dark matter halos around them, and they're living in a galaxy cluster, which is this giant dark matter halo. I'm not sure I fully got the whole question, but galaxies that are close together in a galaxy cluster probably have already lost their own individual dark matter halos. So they are, as a galaxy falls into a cluster, we see pictures here of the gas being stripped. The first thing that gets stripped away is the dark matter around the individual galaxies. So the dark matter gets stripped away, and the galaxies are left behind to interact as they want. The shapes of the dark matter halos are absolutely affected by how a galaxy falls into a cluster, though. The dark matter gets stripped off. So question, I'll repeat it for the audience. The question is, can we resolve the shape of dark matter halos? It is one of the hardest things to do. It's what I did for my PhD. And so what I can tell you is that we can measure them, sort of, but not as satisfyingly well as we would like. So simulations do a very good job of measuring shapes of dark matter halos because they can see the dark matter. Observationally, we have to use some very clever techniques to try to study the gravity along minor axes versus major axes, but it requires some assumptions to begin with about how we think the dark matter is distributed. So the measurements are not great. Yeah.
If we assume all galaxy clusters are red, and we have our own local cluster, and the universe is expanding, and all clusters are moving away from each other, will there be a point where all we see is our own little red and dead cluster in the sky?
Yeah. So the future, we are very lucky to be living in 2023, because we live in a galaxy, but we can see lots of other galaxies. And by studying other galaxies, we have figured out that dark matter and dark energy exists. Many billions of years in the future, dark energy is driving the expansion of the universe to speed up. All the other galaxies we see beyond our local group, they're all going to recede from view. So some astronomer in 20 billion years' time living here would never be able to figure out that the universe is filled with dark matter and dark energy because they would have no external galaxies to look at. And that's how we've learned those things. So feel very lucky to live in 2023 so we can figure that out.
So you talked about the ram pressure stripping with the galaxies in clusters and groups, and just what exactly is it that's causing that? Like, what is the intrastellar or intracluster medium made of? Is it like the dark matter that's doing that? Is it plasma? Is it fluid?
So it's very hot gas, and we can detect it with X-ray telescopes. So I didn't say this, but this image is actually the glowing orange and red is from an X-ray observatory. And so where the X-ray gas is very dense, that's where the galaxies, which have their own gas in them, they encounter this very hot plasma, and it pushes the cold gas out of the galaxy. Very good question.
Well, one thing I've been wondering, I went to some before, although some of it was more about astrobiology with the Origins Institute McMaster. I was talking with someone around Christmas here, and I guess they went to one, but I've looked at the YouTube. I saw there was one about 4 months ago, but they used to have more regular ones. And since you're at McMaster, I don't know what's the state of the Origins Institute or getting them to have regular ones, maybe in person again?
Where one of the primary foci is the field of astrobiology. So bringing together people who are interested in life in the universe. And like all things, they are sensitive to funding. And so the Origins Institute still exists. They organize infrequent talks because that's what they have the budget to do. If anyone is independently wealthy and would like to see more public talks, the Origins Institute is always fundraising. So they would love to have more speakers. It's just a question of financial resources. The Origins Institute has a website, and they post their public lectures there. They also advertise them broadly on McMaster's front page and usually in the Spectator as well. But there's only a couple a year. Yeah.
So, as astronomers, observational astronomers, I don't know anybody in here who does radio astronomy or X-ray astronomy. How can we contribute in science type of way?
So, I wish I had the link with me. My former PhD student, Gandali Joshi, who went to Germany for a postdoc and is now second postdoc in the UK, she helped write a citizen science program to find jellyfish in huge imaging surveys. Some of you may have heard of this project called Galaxy Zoo, where they ask amateurs to classify the shapes of galaxies. So it used to be that surveys were small enough that professional astronomers could sit down every morning and flip through a couple hundred galaxies and say, that's an SA, that's an SBB. Now there's millions of galaxies. So we can write computer software to measure shapes, but there are things the human eye picks up. There are interesting things that humans find. And so now the power of citizen science is used to classify galaxy shapes. And there's a special program which is linked to Galaxy Zoo to find jellyfish. So that's one way that people can contribute, is doing the Galaxy Zoo family of citizen science projects. It's looking through data, yeah. I don't know. Extragalactic astronomy is harder to contribute to as an amateur astronomer, I think. There are more variable stars and supernovae and things in the Milky Way and very nearby galaxies, I think, are places where amateur astronomers have made huge contributions. This stuff, you kind of need the big telescopes. Yeah.
Terrific. Let's hear it.
And as always, at least I didn't go home with it.
Wait and see. That's the page I want. There we go. Okay. So once again, thank you very, very much. And I think we will take you up on that dark matter seminar sometime in the future. Where are we? Yes, galaxy groups and clusters, very interesting. It's studied by many people, in just at least in the observational portion of it. The Astronomical League has a program. As I mentioned earlier, this is the booklet that they use, the pin you can receive, and the address where you can get more information. You don't have to be a member of the Astronomical League to do the program. If you want the pin, then you do need to be in the program or in the organization. Let's see. So we're going to take a bit of a break, get up and stretch our legs. And as you can see, the kitty's having a little stretch. So we're going to take about 10 minutes. Please come up if you want, take a look at the book. Library's open, food bank's open. Make sure you've got your door prize tickets. We have the door prizes at the back table. There are 3 there. We will be drawing 2, so select which you want to use or want to see. So we'll take a few minutes, and I'll see you in 10. All right. Welcome back. I'm sorry, that was a little long on the 10 minutes. That was a metric 10 minutes. Okay. Yeah, yep. Let's see. So, what comes up next? Door prizes, the goodie time. We have 3 items of note. We have the Buzz Aldrin's book, Men from Earth. Very good book. It's a used copy. I think this will be its 3rd or 4th pass me on. The Stars by H.A. Ray. Very good instructional book. I love this book. This is the book that way back in grade 5 I got a hold of, and I managed to get my own copy of it, and I've always had at least 4 copies of it in every edition. Very good for somebody wanting to learn the basics of astronomy and the sky, with more emphasis on the sky. The 3rd item is the Firefly Planisphere. Every astronomer or stargazer should have one. Learn how to use it. It's great for viewing the sky. Now, there are 3 items there. I'm going to draw 2, or I'm going to have 2 numbers drawn. So you get your choice of the 3, or if you're second, you get the choice of whatever 2 are left. So I will end up taking 1 home. Now, I need a voluntold, and it's going to be you, because you're nice and close. Come on up here. You were also the last one through the door, and I don't even know your name. Victoria. Victoria. Let's hear it for Victoria. There we go. Victoria's mother just a few days ago took a membership and has decided that instead of it being an individual membership, it's going to become a family membership. So there. I need you to stick your paw in there and draw out a number. And we're going to read the last 3 digits. 084. 084. That's yours? Go over there, Robert, and see what you need. One more, please. 068. Hello. There you go. Okay, thank you much. Thank you, Victoria. Sorry, I shouldn't embarrass somebody without warning, should I? Pardon me? Not twice? Oh, come on. Okay, so that now brings us up to Steve. Actually, no, I've got to say a couple of things because usually we've ended the meeting. Did you get a chance to get outside and see what the sky's like? Okay. It looks dark, doesn't it? It's dark outside. Okay. I would like first to say Happy Valentine's Day. It's coming up next week. Please don't forget the ones that you love. We also have next weekend Family Day. Family Day weekend. Please bring your family to the Scope Clinic. And a last reminder, tomorrow, I will be, if we're going to go, I will send a MailChimp message out advising if and when the Binbrook's going to be open for viewing the comet. Whether you have a telescope or not, this is a great chance. Come on out. I'll let you look through my equipment if we're there. Something not to be missed.
And the zodiac light, too.
And the zodiacal light, yes. Okay, so Steve is up next. Where are we here? There we go. I presume he'd be all set up here as soon as Sue gets him set up. Mm-hmm. And while Sue's setting up, there will be, to my knowledge, there will be a scope giveaway next month. I'm not going to tell you any more than that for now. The details will be in the email announcing the month.
Do you have to be here in person for that?
Pardon me?
Do you have to be at
Yes, I'm afraid you have to be here in person because I'm not dragging it anywhere. All set? Good stuff. There you go, Steve.
Thanks for your great introduction, Bernie. So I'm your observing director, Steve Germann, and this is my presentation. a good day, this thing here, when switched on, will advance to the next slide. I think we have to click on it. That's probably why it didn't work. Okay. Yeah. So as mentioned, tonight, when it's clear, we're expecting to be able to see our favorite, how should we say, the comet of the month, whose name I won't say out loud, which is going to be very near Mars. Oops, don't push that button, push this one. So you can see this is only like 1 or 2 degrees from Mars, so it's well within the field of view of a decent pair of binoculars, and it should be around 5th magnitude, which is actually pretty hard to see for a comet, but we're going to give it a good try tonight. We're not the only ones who've been looking for and at the comet. We have some pictures here. This one was by our member Chris. Chris, do you want to say a few things about this picture? So this is a 5-second exposure. And Chris managed to point his telescope after maybe several tries in the right direction and caught the comet here. You can see here it is beside probably 7th magnitude stars. It's fairly dim, but it showed up, which is great. And that was on roughly the end of January. And then we have 2 pictures by Bob Christmas. And you can actually see the greenish tinge here. And on a good day, I think I can zoom this thing. Let's see what happens if I go control up arrow. Nothing happens. We got a plus sign up there? So if anybody ever claimed it was a green comet, they would be right. But how long was this time exposure, Bob?
This is a stack or a composite of 13 exposures of 5 seconds each.
Okay, so this is roughly a minute. And so, I mean, obviously, when the camera averages and stacks photos to get something, you're going to see a lot more detail than you can with your unaided eye, which is basically doing stacks of around 1/10 of a second. So this is like 600 times more light than we're going to get. But that won't stop us from, how should we say, getting a good look. Now I'm going to try zooming this thing out, or at least going to the next frame. I've captured myself. Okay. We're going to use the mouse. Only when you're finally zoomed all the way out can you go to the next frame. And so now here's Bob's other picture, I believe. Is this yours, Bob, or was this? Okay, this would be John Govreau. Now, John is actually on Zoom, and he took 3 pictures. I can, how should we say, ask for Chris to nod if he thinks that we're going to be able to hear John. He's pushing buttons right now. John, if you want to unmute and say a few words, we're going to hear. Okay, so John is going to, how should we say, inform others at another time. But today we have 3 photos that John managed to take. Actually, I could be dead wrong. These are Matthew's photos. Matthew's not here today. I believe what Matthew did was he pointed the camera at the sky at the right altitude, and he just panned it left to right and took pictures until one of them showed up the comet, which gives you some idea how hard it is to see. And if we see it tonight, it's going to be because we've got Mars right beside it. But in the middle of a dark sky with no stars, we got to give Matthew a lot of credit there. Okay, I don't believe it's John's photo though, so it's kind of academic. I'm sure John's shaking his head at me right now. Okay, so moving right along. This shows that tomorrow morning at about 5 a.m., the comet will be about as close to Mars as it can get. And it's actually slowly going from basically north to south towards Mars, towards the ecliptic, as it scoots out of the solar system. This is an extremely long period comet. We're not going to see it again for 50,000 years, so this is definitely worth it to try it now rather than wait for the next time. Here's another picture from a different publication showing the same information I'm just trying to show you with my moving red dot. And it's interesting to note that when they write when they make the little mark there, that's for the beginning of the day, not the end of the day. So, or actually, I'm not so sure of that. I think that's that's the beginning. Today is the 10th. The comet is going to be about here. And during the 11th, in other words, tomorrow morning, it's going to pass by. So in the marking, which they don't tell you anywhere, and which I can forget very quickly, is for a day that ends at the mark. So the 11th ends down here, and that's where the comet will be. So it's actually, there was no caption on this picture. So in order to actually look at it and figure out what you were going to see, you had to have other information. So you always have to be careful that, when you make a remark about astronomy, that people might not already know what you're talking about, and you have to put some extra detail. So now it turns out that there's actually, if you're willing to photograph comets, like the photos we saw, there's actually 3 comets of comparable brightness in the sky, circumpolar, right now, that could be photographed. These are dimmer comets than our E3 comet, and we're not going to see them, for starters, partly because I'm not going to try. But this is like 8th magnitude. So 8th magnitude comet is really hard to see. But there are 3 of them in the sky right now. For any astrophotographers, you should move on after you've taken a picture of E3 and get yourself A2 and V2, which is also, you can see here, it's right beside Cassiopeia. That's circumpolar in our latitudes. Both comets and, of course, E3 are good photographic targets right now. And so this is from our website. It's the Hamilton Clear Sky Chart. And I just want to go over it for a minute or two to explain how it works. So the Canadian Weather Service, paid for by our taxes and maybe by printed money, basically computes predictions of what the sky, like basically what the cloud cover is going to be for the future, usually about 36 hours in advance. And then Attila Danko is named down here in small print, A. Danko, wrote a script that basically for any given geographical position extracts 1 pixel out of these giant weather maps that the Canadian Weather Service is making for once for every hour. And he takes 1 pixel out of the map for each hour, and he expands that pixel up into one of these little boxes here. So if you were to see the whole map, and you can actually click on one of these boxes on our website, and it will bring you to the whole map with a little yellow crosshair on Hamilton. This is for Hamilton, where we are. Now, technically, we used to have it being Binbrook, like right exactly where we observe. But what was happening was that, how shall we say, civilians were coming to Binbrook and crashing our star parties without being members and causing all kinds of disruption to the neighbors and so on. So we actually asked Attila to move the dot away from where we actually observe. Now, I mean, these are computer predictions. They're, how shall we say, your mileage may vary on their accuracy. And we're going to see tonight how good they are. Because right here, we are on Friday the 10th. It is around 9 p.m. So this slightly whitish blue dot represents the sky over this area, well, over a selected area, roughly I don't know, 2 kilometers square, somewhere in downtown Hamilton. So you can see, though, that there is a fair bit of dark blue here, and especially tomorrow night, there's going to be a lot of dark blue up here and here. This one here is the phase of the moon. So the bottom line here where it says darkness, you can see that right now the moon has not yet risen, or if it has, it's not starting to light up the sky yet. So this column here for 21, and especially for 22, is going to represent what we're going to, it's the prediction of what we're going to see. Now, this is a fairly early in the chart. Like if you're way over here, forget it. You know how good weather reports are for tomorrow's weather. But this is basically tonight's weather. So you would expect the, how should we say, the accuracy to be correspondingly better. Now, one of the other things that their disadvantage is they're really good at simulating how much humidity is in the air, but they're not really good at figuring out whether that humidity is in the form of clouds or just clear, moist air. So we're going to find out tonight which that is. But anyway, this tool here gives you a good idea of whether, I'm not going to say whether it's worth going out to look, because it's wrong often enough that it's worth going out even in the white sections, but at least to check the sky yourself. But this is a very good tool for our website, and it's a service provided by Attila, and we send him a donation once a year to help cover the cost of his server. This is the next thing I wanted to mention. When we're in town, like here near Hamilton, it's a lot easier to see stars than it is to see galaxies and comets. And I wanted to call your attention, I mentioned this in the EH article, about these double stars that are in a similar arrangement to the famous winter hexagon, Rigel being a double star. And we're not talking about Sirius here, but near Sirius there is another double star. And near Procyon there's a double star. Castor in Gemini is actually a double star, as is one of the stars in Auriga. I'm not sure which one that is. And a rather obscure-looking star near Aldebaran. But the key thing is, double stars are much more satisfying, even in light-polluted skies, than any other things. Now, these stars are not impossible to separate. And here's an example of someone making a sketch of Castor, where he could see the two brightest stars and also a red dwarf not far away. So I'm recommending that if you have a telescope and some time and find yourself under clear skies, which you might well do tomorrow if you come to Binbrook, have a go at some of these double stars in the EH, and especially Castor. It's easy to find that one. It's on the Gemini twins. Star on the upper right is good first step. And then, of course, Sirius. Now, the thing about Sirius, I don't have it here written. Sirius has a very dim, well, not actually very dim, it's very bright, but it's dim compared to Sirius. They call it the pup. It's a white dwarf star that orbits Sirius with about a 50-year orbit. And it's as far from Sirius as it's going to get. So it's going to be an armchair object one of these days. And you can beat it to it by taking a good look tomorrow. But it's very, very rare that people can actually see the white dwarf beside Sirius, because Sirius is so bright. You have to, move it to the edge of the eyepiece. All your optics have to be clean. There has to be good seeing. I don't know how much luck is involved. I've never seen it, but it's going to be worth a try sometime. So now I'd like to talk a little bit about what's going to happen in March. Every year, clubs like ours talk about the Messier Marathon. Charles Messier was a comet hunter. Back in the days when they didn't have telescopes and cameras, he looked for comets because if you found a comet, you could name the comet. And if I find a comet, I'm going to name it Elon Musk, because he might send me $1 million and say, thanks for naming the comet after me. And that's how people like Barnard, the famous astronomer from the last century, he found 6 comets, and he got enough thanks from rich people that he named them after, that he was able to build his own house with them. So it's not a, how should we say, an entirely armchair activity to find comets. Nowadays, though, like I found a list of comets. There's so many. They just go on and on. But if you find a good periodic comet with like a 30-year period or something, there's money in that. So the Messier Marathon, Charles Messier was a comet hunter, but he would find the same comet every day, and it wasn't a comet. It was like a galaxy. So he made a list of all the places that look like comets that aren't. So that whenever he found something, like he was just scanning the sky every night carefully, watching for fuzzy things to go through the eyepiece. And when he found one, he would say, oh, no, that's just, M13. And he would keep going. But before he made the list, it was like every day, it was like, oh boy, I think I found a comet. And then he would have to go and check all kinds of star charts and stuff and then find out that it was, how should we say, not going to move, not going to get brighter, not going to grow a tail, not going to pay the bills. So all the Messier objects, though, were found in a certain part of the sky. In other words, the part of the sky he could see from Paris. And it turns out, by luck, there's a part of the sky where there are none. And that part of the sky is near the sun during the month of March. So when the month is March or early April, if you look in the sky at night, you're going to be able to technically see all 110 different Messier objects in one night, because as the Earth turns, first you see like basically all the way down here, and then when it turns back down here, you can see like there. You don't just see half the sky, because half the night you're looking this way, and then you're looking that way. So there's a lot more than just half the sky available on any given night, provided you're willing to wait for the Earth to rotate. So there's actually a way to basically get organized and set up your equipment before the sun sets and see all 110 Messier objects. And some people have done it. It's a lot easier to do from places like New Mexico, where the sky is clear and the horizons are dark. But I have tried it, and I think I got 95 or something. Pardon, Jim? Yeah, it's warmer in New Mexico too. I mean, obviously March, we can't move March right now. It's kind of stuck. Now, if you wait 13,000 years, it'll be just as hard, I guess. Oh well. Yeah, we want to move it to summer. So you got to wait about 7,000 years, and then March will be in the summer. That part of the sky will be in the summer. So the key thing about the Messier Marathon, though, is you need the new moon, because you don't want the moon interfering with your seeing the galaxies. So the 21st of March is the ideal time, the 20th or the 22nd, if you can find a clear night to do it then. But any one of these last quarter moons aren't too bad, especially the Saturday night there, or even the 25th of March, where a little bit of a setting first quarter moon is not a big deal for the Messier Marathon. It's not throwing light all over the sky, and you will be able to see everything. Oh, and this chart here shows where all the Messier objects are, and it's kind of a busy chart, but the most important thing I wanted to emphasize was this triangular region down here and over here, where basically there's no Messier objects. That's the part of the sky that the sun blocks, that you can't see because the sun is basically here on the ecliptic blocking this area. So as the sun sets, then you can very quickly see Andromeda Galaxy and the Triangulum Galaxy and M77. And if you can catch these four objects, which will be reasonably high on the sky, even in March, but the sky is still, in twilight, then you can work your way across the sky and get all the way to the Virgo cluster, which rises around midnight. You don't have to wait until morning to look for these. And then the last ones here are the hardest ones, because the sun is starting to rise and the sky is getting brighter and you're trying to fish up this thing. But it's an excellent, how should we say, lifetime goal to do the Messier Marathon and see them all, or at least to try. And there's also, how should we say, subsets of the Messier objects. You can have a binocular Messier Marathon, where we extract out all the dim galaxies that you're not going to be able to see with binoculars and only expect you to find the ones that are visible. Then there's like 75 objects instead. Okay, so this month's armchair challenge is the zodiacal light. And I can say that I have seen it. It's actually annoying when it does show up. But this is an image of the zodiacal light in a photograph that I stole from the internet somewhere. And I don't usually attribute my photos. But you can see that it's got like a, sorry, back up. It's got like a brighter band here, and it's a bit like a triangle. And it comes before the dawn. Like you can see a little bit of twilight there on the horizon, or maybe some light pollution. But it's quite high in the sky. And it actually extends up here too, but you'd never see it because it gets like 10 times dimmer as it goes across. And here's an image where they actually now believe the zodiacal light is basically Mars dust. So you can imagine dust storms on Mars being so violent that Mars actually throws off, well, we know that Mars has lost all its oceans due to the solar wind. And so it's basically able to lose things from its atmosphere. And they figure that the zodiacal light is caused by this huge sort of disk of Mars dust that's surrounding Mars. Now, I don't buy their claim that some of the particles that have come off Mars are a meter in diameter. You're not going to blow that off of Mars with solar wind. So there's an element of how should we say, poetic license there, but this was the Juno probe. When it was passing through Mars's orbit, it was very carefully watching for specks, and it calculated their profile. And this is a frame from a video that basically shows an animation of the whole process. And a good day, we can go to the next slide, but we can't, because that is the end of my talk. Basically, you're invited out after our meeting to the parking lot. Usually we have the windows open. I don't know why the curtains are drawn today, but there is a sort of a darker section of the parking lot on the far side, and I've parked my van there, and I have a set of 25 by 100 binoculars, and we can set them up for anyone who wants to have a go at finding the comet. And the binoculars are big enough that they'll have a field of view. It won't just zip across, and we should be able to all have a good look if we convene over there in the dark. So that's that. And if you're, how should we say, in a hurry tonight, you can always take a chance and come to Binbrook tomorrow and kill multiple birds by seeing zodiacal light. Now you have to be there right at sunset though, because it rapidly dims. So 7:30 would be about the latest time you want to be at Binbrook if you want to see the zodiacal light. Okay, that's it. Any questions? Well, keep your photographs coming to me if you take any pictures. That's all I can say.
I'm just recalling what you were saying. Yes, please. When you were talking about the Messier Marathon, put me in mind of a few years back when a younger Kevin Solwak and I went out in mid-March, and it was just a little on the cool side. I believe it was like minus 27 with a slight breeze of about 15 kilometers an hour. Slight, yes. And we were both using binoculars, and I was using a parallelogram, and it was breezy enough that you get looking at something, and all of a sudden the binoculars went over there.
Sounds like SpongeBob remembering good times.
Yes, yes. But the most fun part of it was one time looking through and freezing your eyelashes to the eyepiece.
I see. So now that you've highlighted all the
all the bad stuff,
forward to
yes. But the good side of it was an extremely clear night. It was a moonless night. We hit it right on the new moon.
Mosquitoes.
No mosquitoes, no mosquitoes, no bugs, no snakes, no anything. No heartbeat either after a while, but
Can't guarantee no coyotes anymore.
I think they were all staying inside the dens. But I forget what was our count. We 95 or something like that. It was pretty good with binoculars. Yeah, these were with 20 by 80s. Yeah. So yes, if you get a chance, do it. It doesn't matter if you get 4 or 44 or 94.
Yeah, and I'm sure we'll have a chance to get out in March
Yep.
on a clear night.
I believe, if you look, March the 17th, Members' Night at Binbrook.
Okay, so let's go back 2 frames to my moon phase, and we'll see. Is it long gone? Long gone. I think March 21st is the new moon. So March 17th is just fine. It's late third quarter. And it should just be, there'll be no moon in the evening, so that'll be fine. Turn this thing off.
Awesome, thank you. Let's see, there's not a heck of a lot. I'd just like to touch again on Scope Clinic coming up next weekend. Okay, still enough to get a whole whack of them. Now, something that I did know or come to realize about the Messier Marathon, it says to observe them all in a 24-hour period. That does not mean sunset to sunrise. That can mean from midnight to noon and then noon to midnight. That's right. Because yes, if you're going to do it overnight, you're going to be sleeping between 11 o'clock and 1:30 so that you can catch the bunch coming out. But it's something worth trying. And the real good part about it, if you really want to test yourself, is you do it without go-tos. Oh yes, well that helps too. Been there, done that. Okay, so let's see. Mentioned 25th is the outreach out in Binbrook. Let's see, what do we have? That's it. That's all I've got. I did mention scope giveaway at our next meeting. You must be here to win that. Details to follow in the EH and in the MailChimp. I wish all of you a very pleasant evening, a good week, a good month. We'll see you in a day or 2 or 3, or maybe a couple hours outside. Thank you.